if we switch the drift like this to change the process such that we can move from numeric asset G to numeric asset H, in this case, we'll have to deal with every single risk factor I if we have a multi-factor process. So it's a little complicated, but if we can define an asset W, which is the ratio of H divided by G, and if we know the correlation between this asset and the asset F, we can actually have a simpler way to switch from a world where G is used as a numeric asset to a world where H is used as a numeric asset. So what do we do? So basically, if initially you have a process basically like this, where G is the numeric asset. Now you want to switch to H. Okay, so define W, a new variable, which is equal to H divided by G. And you can see that by Ito's lemma, dW, if you just look at the random innovation part, the volatility of dW will have this form here. Okay, so just look at, use Ito's lemma and derive it for yourself. You will see that the volatility of W is really the difference between sigma H minus sigma G for each of the factor I. Okay. Now, so you have this. So what happened is this alpha F, which is the term we defined here as a change of the drift, is really, the sum of this part, sigma, all those lambda are just, it's the risk price, it's basically sigma, the volatility. So risk price when H is used as numerator is then sigma H I. Okay, now G is used as a numerator, is the risk price is lambda G, then the sigma G I. So this difference here, as we see, is just sigma W I. So here we're summing over sigma Wi times this. Okay, so we made some progress here. So this change of drift, we can express as this. But then we still have a summation here that we want to get rid of. Now to get rid of that, we have a condition that we say this summation is just the product rho times sigma W times sigma F. Now this sigma W is the entire volatility for the process W, not for each of the individual factor here, okay? We'll see some examples later on. But make sure here there's a difference between sigma Wi and a sigma W. Sigma Wi is the volatility of W for each risk factor I, or random changes, random factor I. Here, this is the total change. This is the total. If we express them as once, put everything together as a sum, this is the total effect, the volatility of all the risk factors together for process W. Okay. Now, how do we associate this to that? Well, okay, and this is the volatility between W and F. Okay. Now, how do I associate that? Well, here we see that what is delta F? Well, delta F is just a whole bunch of drift terms plus this random innovation here, where you have this part is the delta Z for each of the risk factor for each of the random factor I here. Now you can look at delta W exactly the same way, you know, whole bunch of drift term here, and plus this random changes here. Now it's important to notice that they're all under the same set of risk factors. Okay, I. Now, so if you have that, and we know that each of the random factors are independent. So if you have a multi-factor model, in between the risk factors themselves, they're independent. That's why the expected cross term here, the multiple of the cross term is 0. And so in that case, so what is, if we look at the expectation of delta F times delta W, well, this thing here is really the drift term of the product. And the drift term of the product is really sigma Wi times sigma Fi, and then you got the proportional factor W and F here, okay? And you should actually have a whole bunch of cross terms, but you know the cross terms dropped out. So the expectation here is just this straight factor here. So there's no, you know, something times I times J there. Now, so what is this expected product of delta F times delta W? Delta F times delta W is equal to this. And we know also that the expected delta F times delta W is really, you know, you look at the expectation here, by definition of the covariance. So you have a covariance between F and W, which is defined this way, is basically the expected value of the product minus the expected value of delta F times the expected value of delta W. So this is really just by definition here, okay? So the definition of covariance. Now from this definition of covariance, we see that this part actually dropped out in continuous time, because as you shrink the time to 0, you know, as time approaching 0, what is this part? The expected value of delta F is this, you know, the first part related to dt. And here it's also related to dt. So together, they're related to dt squared. So as you move t to 0, you have to shrink that time period. So your dt is shrinking to 0, and the second order dt squared is shrinking faster than dt, so it's a higher order term that you get dropped out. So then at the limit, when delta t is approaching 0, basically this rho times sigma f sigma w is equal to expected value of delta f times delta w. Okay, so now you have this part here. So that means, you know, looking at it together as two processes and looking at them as individual factors, you have a relation that if you know the correlation between F and W, so then you have rho sigma F, the volatility of the entire factor F and the volatility of the entire process W times the correlation is equal to the sum of this. So the two blue ones are equal. Therefore, you basically derived this expression here. Now you no longer need the summation here. If you know what is the correlation coefficient between W and F, and you look at them, each of them as a single process, and you look at what's the volatility of that process W and what's the volatility of that process F, putting all the risk process together, the random factors together, then you have come up with this relation. And then you no longer need this summation. You can just calculate it directly. And then your change of drift here will just be this much simpler expression.